Yeah. Uh, Hello. So, welcome to the sixth class. This is a very important class. So, what I plan to do in the next 1 hour is give an overview of the formalism of Stat Mech. Now, typically, this is not how it is done. Typically, one spends time on explaining microcanonical ensemble, uh, figuring out how certain quantities calculated in microcanonical ensemble can be related to thermodynamic quantities. And thereafter, after 2 weeks or so, introduce the canonical ensemble and then calculate properties of it and relate quantities calculated to thermodynamic properties and giving logic and proof of each of the steps. The consequence is that often over the steps of um, uh, calculations and proofs, one often loses the big picture. So what I'm trying to give today is the big picture of what there's all there to stat mech, and each of these steps of being proving and relating and giving reasons will follow up. So the point is that is all that we're going to do. This is the formalism, and the rest are the details which have to be filled in, after which we're going to use this formalism to calculate a large number of properties. We're going to apply to different systems to understand various systems, and that's also where you're going to understand how StatMech works. But at that time, people are often confused where to use the microcanonical, when to use the grand canonical. There's a lot is going on. So this lecture is to give an overview, not proofs, but help you to build the physical intuition of it. So that's the purpose of this lecture. So let's start the actual content. Having told you what this lecture is going to be about, what you have already comfortable with or should be comfortable with is that there are various, if you have a system, you can define it in terms of thermodynamic variables such as TVP. I mean, we're talking about the ideal gas, and we'll later see. But we can also apply you can also talk about magnetic systems, say magnetization, density, and so on and so forth. And those are macroscopic properties. They are bulk properties. You can feel pressure, volume, temperature, put in a thermometer, and so on and so forth. But now let's go to the microscopic variables. And for simplicity, let's start talking about a box of gas. So at a box of gas with suppose n particles, and then in this box of volume V, which is the macroscopic variable, you have n particles, and at time t1, they have certain positions in space, right? So suppose they are x1, x2. Just one second, let me see whether I can remove this a bit more. Yeah. So the n particles have positions x, y, and z, which I denote by x1, x2, and x3. And if there are n particles, then in terms of position coordinates, you have you can specify x, y, z for these n particles, and that's why I've written x3n. And similarly, you can also specify the momentum, which is P1, P2, P3 for X, Y, Z, and then up till P3N. Now, this is just an instantaneous snapshot of a gas of molecules, right? We also assume it's isolated. There's no heat exchange, and thereby the energy of these gas molecules is fixed at, say, E. It can fluctuate between E and delta E, but it's, I mean, within some uncertainty, but it's basically fixed at E with a slight deviation, maybe between E and E plus delta E, because there's some, because you might not know it exactly, but within your measurable abilities, you know it to your value of E, right? But these are moving. So in the next instant in time, time t plus delta t, So each of these gas molecules would have moved from here to here, and from here, from this blue point to here, and so on and so forth, because each of them have some momentum. And some of them also are going to undergo collision. So each of these set of 3n p variables, momenta variables, and 3n x variables, we're going to call it a microstate. So when you specify all these 6n variables, 3n plus 3n variables, they correspond to one microstate. And as the system evolves in time, one could say that the set of n gas molecules are keeping on updating its 6n coordinates to go from one microstate to the other. So at time t1, if they had these coordinates, at time t2 or time t plus delta t, they have changed positions with x1 dash, x2 dash, and so on and so forth, and they will also have momenta p1, p2, p3. It should be p1 dash, p2 dash, p3n dash, right? And at time t1 plus 2 delta t, they would again have x1 double dash, x2 double dash, p1 double dash, p2 double dash, and so on and so forth. So what is the point? The point is the system is going, all these microscopic coordinates to the variables are going, they're constantly changing, and the system is going from one microstate to the other. Can you see each of these microstates? No. What you feel is the combined effect, or what you see macroscopically in a macrostate is the combined effect as these box of gas molecules move around and go from one microstate to the other, as they change positions, as they undergo collisions, as they collide with the walls of the gas. They keep bombarding you. As a consequence, you feel pressure. You might also feel the temperature of the system, which is related to kinetic energy, as we'll see, and so on and so forth. So a bunch of large number of microstates corresponds to a macrostate. Now, if you have a different box with different number of molecules, they again are going to keep on exchanging position. So you will have a corresponding different PVT, and they will correspond to a different set of microstates as the particles go on exploring configuration space and phase space. So what is configuration space? The 3n coordinates corresponding to the space coordinate, the xyz coordinates. If you consider all 3n of them, they are called the configuration space. The particles are moving around. So as they change positions, they are basically moving around. So in 3n coordinates, that's just a point, right? So usually you talk about x, y, z, but now suppose you could imagine that there are 6n you have 6n coordinate axes. Then the particle is occupying one point in the configuration space. And if you have 6n coordinates corresponding to x bar and p bar, now x bar essentially is 3n coordinates and p bar is 3n coordinates, then essentially the system is moving from point to point in phase space, right? Because they're changing their momenta. Why are they changing their momenta? Because they could be colliding. Some of them will keep on having the same momenta till they collide. So the particle is basically moving around in a 6n dimensional phase space. But you don't need to, I mean, that's how it is taught, and that's why I'm introducing these ideas of configuration space and phase space 6n dimensional. But you really don't need to think about it. If you have problems, no problem. You just think that the system is moving from one microstate to the other as the particle positions and momentums change, because the positions change because they have finite velocities, momenta change because they have collisions. Right? So that's what I've written. An isolated system with n gas particles, isolated, no energy exchange, with n gas molecules keep changing its phase space coordinates because they have momenta, finite velocities, and because they are collisions. Right? Now, they are moving around just to, I mean, even before going forward, just to give an idea of phase space, because that is often conveyed. So I want you to be aware of it. So you have this 6n dimensional space subject to the constraint. So the particles can exchange momenta among themselves. They can exchange velocities and momenta among themselves, right, as they undergo collisions. And they can take any value. They can take very high values and some can take very low values, but subject to the constraint for the ideal gas. Because you have an ideal gas and you don't consider that there is interaction, well, there is a sense of interaction in the sense that there are collisions. If there were zero interactions, the particles would keep on moving in straight lines forever, right? But for the purpose of calculation of the total energy of the system, we do not consider potential energy. So if they were perfectly theoretically ideal, then there would be no collisions. But there are interactions, there are momentary collisions, and some of them are changing their momenta after undergoing collisions. They're traveling large distances. The mean free path is approximately 50 to 100 nanometers, which means that they're traveling the length scale of 1,000 times their own size, because the atom would be typically 1 angstrom, 2 angstrom. And if the mean free path is 100 nanometers, that means they're traveling 1,000 times their own size before they're undergoing a collision. And they're exchanging momenta with each other subject to the constraint that pi squared by 2m equal to the total energy of the system. Why? Because it's an isolated system. You have taken that no energy exchange is allowed. The volume is fixed, there's no work done, there's no heat exchange. So the momenta can change subject to this constraint. The positions can change subject to x, y, and z. I remain within the box, right? So if you were to plot, the phase space coordinates, right? So let's look at only the momentum space. So if there were two particles and they were isolated, then you would have the total energy equal to P1 square with 2m1, P2 square with 2m2 if they had different masses. And if they had the same mass, then this would also be m1 equal to the energy. And this is an equation of an ellipse. Now, if you had three particles, then you would have P1 square by P2 square by 2m here, P3 square by 2m. Here I've taken all the masses to be the same. And that equal to energy, equal to E, the total energy of the system. And this would be a different value, but whatever. I mean, it could be the same, whatever, right? But as they undergo collisions, P1, P2, P3 can change, but the total sum has to be the fixed. And this is the equation of an ellipsoid, right? There's the constraint. So it's basically, it's a surface. I mean, if all of them were the same values, then it would be a sphere. But if P1 square, P2 square, and P3 square can vary and interchange among themselves, then basically these particles are moving on the surface of an ellipsoid. Okay? Now, if you have n particles, you essentially have an ellipsoid in 3-dimensional space because total energy is conserved. Right? So that's the picture I want you to have. That's how the phase space is going to look. You can imagine for 2 particles and 3 particles in the extended, except that it will be a sphere in some hyperspace or whatever, right? So because these are constantly exchanging among themselves and the total energy is fixed, which is the most important part. Now, let's introduce the idea of ergodic hypothesis for equilibrium. So you are assuming equilibrium, the system has reached equilibrium, isolated, no energy exchange, right? System. Just to remind you, what is equilibrium? A system left to itself, an isolated system, relaxes to equilibrium, as you saw thermodynamically when entropy in thermodynamics, when its entropy is maximum. And what is equilibrium? System independent of time is not enough. Once it is relaxed, it's not enough. It could be a driven system, right? Of course, an isolated system cannot be a driven system. It will relax to equilibrium when it has reached maximum entropy principle. But in general, even if you had a system interacting or exchanging energy with the environment, the condition for equilibrium was no net current in this system. Right? There will be no net current in the system. If it was isolated system, right, then it would be basically the density would be uniform all over. There's no particle density, there's no momentum density. Particles could be moving from this point to that point, from this point to that point, but there will be no net particle current. So if 3 particles move from here to there on an average in a small window of time, 3 particles will move from there to here. Right? So there's no net current. So here the word net is also important because particles can move. Right? And as I have given an example previously, like a bar. So here it can exchange energy, of course. This is not an isolated system, and a metallic bar between temperatures T2 and this should be T1. I'm extremely sorry. Then there would be a heat current through this if the 2 boundary conditions are maintained at T2 and T1. And after a long time of the system relaxes to steady state and not equilibrium, the temperature gradient will be like this, but there will be a heat current, and hence the system is a steady state and not in equilibrium. Right? You could also have gas molecules which have density variation, as in the atmosphere. As you go up from the surface of the earth, the density of gas molecules decreases, right? And assuming no wind and no current and no heat, I mean, if you could consider that, practically there is always wind and temperature gradients and so on and so forth, but assuming over a certain height, then there is a density gradient. But again, if there's no wind, if there's no heat current, there will be no current of particles. And then you could consider it under conditions of relative equilibrium, right? But in an isolated system, it's much more easier. It will relax to equilibrium once it has no current, and then entropy will be maximum. So that's equilibrium. It's important that it is isolated system. This discussion in blue was basically just to remind you what equilibrium was and to make this lecture self-contained so that you don't have to refer to previous lectures just to remember what is equilibrium. And the ergodic hypothesis is that all microstates are visited. That means as a system moves from one position, as the particles of the system, isolated system, move around within the confined volume, because you have specified the volume, and exchange momentum with each other. And there will be a huge number of microstates. And it says that ergodic hypothesis mentions that all microstates are visited, and visited with equal probability. There's no bias between them. If particles are going from here to there, particles are also coming from here there to here. And moreover, the ergodic hypothesis is all microstates are visited, and any thereby any microstate can be occupied with nearly equal probability. The second part is the postulate of equal a priori probability or something like that. I think it's written down in the next slide. Here I want to say that not all systems can be ergodic, need to be ergodic. There can be certain systems, glassy systems in particular, and we are not going to discuss glassy systems, which are non-ergodic. So all microstates are not visited with equal probability, right? So just to ergodic postulate of equal a priori probability is that all microstates will be visited with equal probability, right? So it means you could have a microstate 1 within V, E, and N, which is specified isolated system, that all gas particles are in one corner of the room. That's one microstate. And you could have a microstate 2 where all gas particles are spread all over the room, right? There could be a microstate 3 where the particles are spread all over the room, but all of the particles have exactly the same speed, maintaining this constraint, of course. That's also a microstate, right? But you know that in reality, you have the Maxwell-Boltzmann distribution of velocity. And now I am claiming that all microstates are visited with equal probability. So the probability of accessing any microstate is equal, right? So this is a very important postulate of statistical physics. That first of all, there are many microstates, and in an isolated system in equilibrium, the both isolated and equilibrium is important, saying that all microstates are visited with equal probability. Why is it that never in your life have you ever seen that gas molecules are all in one corner of the room and you choke to death? Right? There seems to be a contradiction, but let me explain to you why it is not. The reason is, and this is a very crucial point, the number of microstates available when the volume of phase space, that is the volume of phase space available when particles are spread out, is supposed 10 to the power 100. The number of ways the particles can arrange themselves in different ways, right? So that's essentially what when they are all spread out is much more than the number of microstates available when all the particles are huddled together in suppose in one corner of the room, right? So within this volume, if all the particles are huddled together, the number of ways they can arrange themselves, the number of position coordinates they can occupy as they keep hovering around here is a relatively small number. I mean, it's a huge number, don't get me wrong, it's a huge number, but small compared to the number of ways that they can arrange themselves in real space, let's think, and it's the same for momentum space, when they're all spread out, and when they're all spread over. So when they're spread over, the number of position coordinates they can access, say, is 10 to the power 100. And when they're huddled, let's say, the number of microstates they can access is 10 to the power 50 only, right? And all of these microstates have equal probability of access, right? So they will all, so each of these 1 into 10 to the power 100 and 1 into 10 to the power 50 have equal probability of access. So what will they do? They will all be basically most of the time spending and exploring microstates out of this 10 to the power 100. What is the total number? I mean, this is just like I divided into 2 volumes. Of course, it's not like that. I'm just giving you the idea. So the particles are busy exploring 10 to the power 100 microstates with equal probability rather than explore 10 to the power 50 microstates. What is the probability of being in a small corner of the room? It's 10 to the power 50 upon 10 to the power 100 by 10 to the power, sorry, this should be again 50. 1 upon 10 to the power 50. So you're never going to find yourself choking to death. And you are not violating this hypothesis. That hypothesis is true. And there's no reason that you're going to find in your lifetime all gas molecules in one corner of the room. I just want to emphasize this example is indicative. Proper calculations will follow. The how many microstates do you have as things are spread out, right? So even in terms of intuition, even if all microstates have the same probability, and that's an input, right? That they are going to keep on exchanging their positions, and there's no reason for you to think that any particular microstate is favored because they will collide, sometimes exchange more energy, less energy, as long the sum of the total kinetic energy is conserved, p square by 2m, because it's an ideal gas with collisions, right? So it's an assumption that the system is ergodic, and postulate of equal a priori probability is saying that all microstates are equally probable. And why should we believe it? Maybe some microstates are more probable, especially if there is a interaction, maybe some. The reason is if a system is isolated, and if you calculate quantities and compare it to thermodynamics, and from here go further ahead and look at systems which are not isolated, because most of the world around us, we exchange energy. This room is exchanging energy with its environment, right? The consequences that are going to follow after this, they match with not only your intuition of nature, but measurements, accurate measurements of nature. The proof of the pudding is measurements. You can have 1,000 theories, 1,000,000, multiverses, doesn't matter. Is it true or not? Is the final question you're going to ask, right? Until date, yeah, I mean, of course, we are teaching this because since it was proposed, and if you have systems, you have found systems which are non-ergodic, right? And there you cannot apply this theory the way you are doing it now. And then you say, okay, so how do we deal with non-ergodic systems? But at the moment, we're dealing with simple gas molecules. They are ergodic, their properties, and we will derive PV equal to nRT, right? Okay. Now, so this is this. So what I have at the moment introduced to the idea that if a gas molecules isolated in equilibrium, system is ergodic, and postulate of equal a priori probability that all microstates are visited with equal probability for an isolated system. Now let me introduce the idea of an ensemble. Okay, so I hope you have realized that a system of ideal gas molecules wanders around in phase space, changing its positions, 3n coordinates, and momenta, another 3n coordinates, as a function of time, subject to the constraints of E, V, and N, right? So as a function of time in phase space, there's a point, and this point is moving around on the phase space. And if you're looking at momentum, it is moving around on the surface of a hypersphere. It can take any position, but as long as it is on the surface of the hypersphere. Why does the hypersphere come? Because the total energy, they're just expressing that the total energy is conserved. That's all that you're saying. Your P1 square by 2m plus P2 square by 2m plus n, 3n, they're conserved. It has a fixed value. So that's all that you are saying by all this hypersphere business. You don't need, if it's difficulty, don't need to visualize it. But you can follow a system as a function of time. And here you have to use your imagination. What you do, suppose there are 1,000,000 of you, and each of you writes down its phase-space coordinates, that is x and p, at a different instant in time. So he writes, as a particular student writes it at time t1, a particular student writes it at time t1 plus delta t, third student writes it at t plus 2 delta t. Right? So each person is writing down the microstate coordinates, the phase space coordinates corresponding to a different microstate, and writing it down, right? And then you collect it after 1 hour. So each has a different set of coordinates corresponding to different microstates, right? And you submit it to me. So what I have, a set of coordinates for different microstates, but however I can look at them, if I can, all together. So you have essentially, I have a zillion copies, zillion pages where different x and p's are written down, and each page where you have written it down corresponds to a different microstate. This collection of such imaginary zillion copies, I can't fit it on my table, that's why I'm saying imaginary. The collection of such copies of the system, where you write down, where each copy corresponds to a particular microstate, the collection, the set of all these microstates correspond to an ensemble, and you can look at them, if you can, if it is superhuman, at the same time. So if I have an ensemble, if I have, so one thing that one thing is, an observer could look at a system over next 1 hour and let the system and observe the system as it explores its different microstates. The other person says, oh, I have a zillion students. They have all written down the coordinates of all the different microstates. What I'll do is not follow the system over time, but I have a fantastic computer. I'm going to calculate the properties of the system by using all these coordinates. I'm going to take an ensemble average, right? So I have the same time. I'm looking at all of these systems. There are these n copies of this system where each copy corresponds to a different microstate. And I can calculate the statistical properties of a system, say the speed distribution of particles as the particles collide and move. Speed distribution, you can either calculate it an average over time and get the speed distribution, or I have these zillion copies of the system. As the system goes from one microstate to the other, I say, oh, I'm going to just use this and calculate the average properties of the system. So this picture where you have a zillion copies, where each copy of the system is in a different microstate corresponding to the same macrostate. Most important is all these microstates, an ensemble of microstates correspond to the same macrostate, right? That is an ensemble. And here, so as I said, you could either do a time average and get the properties, the macroscopic properties of the system. Well, the theorist will say, oh, I'm not going to follow it over time. Instead, I'm going to take an ensemble average, because I already have zillion copies of this system. This data is available to me. And I'm going to take an ensemble average and calculate the thermodynamic properties, right? But the experimentalist is going to say, okay, you have all these copies, but are you sure that what you calculate and what I measure, they're the same? You can say, yes, I'll calculate it correctly because I'm basically following these different microstates. And the second input to statistical physics is that the belief that ensemble average is equal to time average. There's a belief, you just input it. And why do you believe it? Because when you do an ensemble average, you get or you match results which are calculated the time average in the lab, right? So as I said, theoretically, you follow a system over time and measure its properties. Theoretically, you can do an ensemble average. And those of you who are doing the computational physics course, when you will be doing a Monte Carlo, you will be basically generating different microstates and do an ensemble average. And when you do molecular dynamics at the end of the course, you'll be doing a time average where you'll follow a system over time on the computer, however. And so molecular dynamics is integrating Newton's equation of motion and following a system as it evolves as a function of time. On the other hand, in Monte Carlo, you're going to use stochastic methods and random numbers to generate different copies of the system, different microstates of the system, and do an ensemble average. Okay. So in the computational physics, you can do both depending upon which is your convenience or depending upon which question you are asking and so on and so forth. Right. So as an example, suppose you wanted to calculate the kinetic energy of a particular particle. So what you could do is take a particle and follow it if you could. Well, you can do these, if not for an atomistic particle, you can do it for macroscopic particles. Macroscopic, when it's a macroscopic, I mean 100 nanometer size or so on. They can be colloids, Brownian particles, and so on. So you can calculate the kinetic energy of a particular particle, the ith particle, over time. Or you say, okay, there are many copies of this system, and these various in these various copies of the system, this particle has this much energy now, and that much energy, kinetic energy now, and that much kinetic energy in another realization of the ensemble. So the ensemble is the collection of all these, right? And thereby you can calculate the ensemble average. And the claim is that kinetic energy, time average, and kinetic energy of ith particle ensemble average are equal. And this assumption, pretty big assumption, but it's proved true by experiments. Hence, it's an input to the theory, right? In general, you can say that the kinetic energy average value, ensemble average, is the probability of finding the entire system in a particular microstate, probability that the system is in that particular microstate J, and what in that microstate, what is the kinetic energy of particle I? And you sum over all microstates. And we are summing over the ensemble of microstates, all different microstates, and each different microstate, it could have a different kinetic energy. Well, some set of them, if it hasn't undergone a collision, it will have the same kinetic energy, but once it has, it will change, and so on. So you are basically copying. So you're basically taking an average over all possible microstates. And of course, if you have an isolated system in equilibrium, we said that the probability of accessing each microstate is the same, right? Which is the postulate of equal a priori probability, right? So that's the idea. Now the question is, okay, these are good ideas, but how to connect to thermodynamics? Can you calculate the total number of microstates at fixed E, V, and N? Now, if space is supposed to be continuous, then you will have infinite number of microstates. But let's suppose discretize space, and later it will be found that we're going to discretize it by the H cross constant. That is going to come after 3, 4, 5 classes I do. Okay, but at the moment, taking a certain discrete value of the size of the phase space, I mean the basic unit of the phase space, which later will turn out to be H cross. So can you calculate the total number of microstates at fixed E, V, and N? The answer is yes for simple systems. You can do it analytically for simple systems. Sometimes you have to need averages in more advanced techniques. And if you call the total number of microstates to be omega, then, and if you could calculate it, and we'll do it in 1 or 2 classes for the ideal gas and then for other systems, then S, then if you take the log of omega, the total number of microstates at fixed E, V, and N, and when you are doing it at fixed E, V, and N, it's called the microcanonical ensemble. And later you will have other ensemble, which I'll soon introduce. And if you take the log of it, then this quantity behaves like the entropy. How and why? We'll prove it. But at the moment, in this overview class, just accept it. So the question is, why and how will log of this total number of microstates, irreversible process, reversible process, additive properties, does it behave like entropy? We'll come to it. That's why there are so many classes. But at the moment, if you replace it by a proportionality constant, I mean, so this S behaves like log of it, and Boltzmann wrote it down as S equal to K ln omega, omega being number of microstates for an isolated system with fixed E, V, and N. And later this was found to be Boltzmann constant. But initially you don't know a priori. And as I've written, the quantity, this quantity K ln omega behaves exactly like entropy. And so let's identify it as entropy, right? Now, number of microstates, if you change N or you change V or change E, then it will be able to, I mean, if you increase E, suppose, then it will be able to access a larger number of microstates. So you are calculating the total number of microstates at E, V, and N. And when you take its log, the entropy itself will be a function of E, the internal energy, the total energy of the system, the volume, and the N. Okay. And if you believe and if you convince yourself doing a sort of calculation, seeing that it has the similar properties, and of course the question remains, what is K, right? And we'll take up a few classes. If you can get this in an exact closed form, and you can get that for some cases, right? And this is a function of E, V, and N. And then you can calculate del S, del U at fixed volume, right? So from this relation at fixed volume, because you have fixed volume, say if you changed energy a bit, how much would the entropy change? And that you would see has the same, you identify it as temperature, because you have S, you have identified this with entropy. That's the first step. That's what Boltzmann wrote down, and he faced a lot of flack for it. But gradually it was proved to be true. So the way you calculate temperature in this system, so you say, okay, you have an isolated gas molecules, ideal. You can calculate its entropy in terms of E, V, and N, and E is the internal energy. You take its derivative. it will be 1 by T. And if you take its derivative with respect to volume from here, right, at fixed internal energy, you will get pressure. So in an isolated system with fixed EV and N, if you can calculate the total number of microstates, we call it entropy or relate it to entropy, and we'll be doing this slowly. And then entropy is a function of EV and N and other thermodynamic parameters. By taking suitable differentiation, partial differentiation with the appropriate variables, you get the values of 1 by T and 1 by P. Right? And if we could write it down exactly, this in turn will give you PV equal to nRT, but we'll wait for that. So as I just said, this system, isolated system, is the microcanonical ensemble set of microstates at fixed E, V, and N. The probability of accessing different microstates in a microcanonical ensemble, it already assumes equilibrium. All microstates have equal probability. Hence, the probability of accessing any one particular microstate is 1 by omega, the total number of microstates. And S equal to K ln omega E, V, and N. And if you have that, and if you can write down that, and if you can calculate that, then by taking suitable derivatives, you can get P, T, and any other relevant thermodynamic quantities. Okay, so that's the microcanonical ensemble. Immediately after that, I want to compare it to a very slightly different case where energy when a system can exchange energy with the system. And for that case, it's called the canonical ensemble. But though I want it just back to back, though in a proper stat mech course, it comes after 4-5 days or 6-7 days. But here I want to tell you back to back, so can directly 1:1 compare. And at the end of this, it has a chart. But I'll just put it in a different recording. Okay, just next recording.